So I'm presenting this paper that I am on that was done at Laser Labs. London AI Safety Research is one of these fellowships you can apply to. It's similar to Matt's. It was done in London with three of my co-authors and a couple supervisors. The main supervisor being from the UK AI Security Institute. Um, and yeah, so last time I just like gave more general background on AA control. I talked through the foundational paper on it from a couple of years ago. I'm just gonna quickly speed through that, just so we know we have the shared context. So by control, we mean we ensure that even in the worst case scenario where all your models or your most strong model is scheming against you, is like actively trying to subvert you at every turn. Do some capability evaluations to based on your safety measures to see what your risk is. So it's distinct and complementary to alignment. Alignment, is try to ensure you're not in that situation. Here, we're going to assume our models are maximally egregiously misaligned and see what kinds of protocols can ensure safety. Um, and so the general setup is we'll have this kind of powerful, untrusted model. It's drawn as purple, not red, because like it might be scheming against us, it might not be, and we want to ensure safety. Despite that, we're also assuming we have some trusted models that are like pretty weak, like basically, uh, you know, think like GPT-4, maybe GPT-5, th things that are probably not keeping secrets of us, and are probably not like wildly egregiously misaligned to the point of, planning backdoors or lying about backdoors or something like that. And so the sort of threat model we're imagining is we have this powerful untrusted model that's internally deployed at a frontier AI company. It's like writing, we're just like vibe coding all our capabilities and safety work, and we want to ensure that goes well at minimum risk to it planning a backdoor or something like that. And because it's writing so much code, like maybe a billion tasks in its lifetime, and it's only a small percent of that, we can realistically read carefully. Yeah, we want to ensure that kind of goes well. So we want it to, not gain root access to a data center or copy its model weights off server or poison some training run or do something else. Um, so we're going to just abstract away from that and just think of like monitoring processes that can reduce the risk of that sort of thing. And we're just imagining an untrusted model that's quite a bit more powerful than current things. That it's coding abilities are like actually across the board uh, quite good, like not just on benchmarks, but it's actually like doing everything that best humans can, but better, and that's also good at reasoning about a situation, coming up with good strategies for doing bad things, and that it kind of knows what our protocols are. So it has very strong situational awareness. And so our methodology is like we do the blue team, red team game, where the blue team proposes a protocol, and the red team proposes a strategy that minimizes safety against that. Safety being the probability that our untrusted model, assuming it's trying, it's not able to plant a backdoor during its long deployment. So there's like a blue team win rate and red team win rate, and they're like they're directly at odds with each other. And we also, don't want to ruin usefulness too much. Um, like we could just use weak trusted models for everything, but like that'd be like 0% usefulness. We don't want to do that. Um, so that's sort of the framework we're working in. Um, and then the original paper and our paper both use the apps data set of programming problems. Yeah, 5,000 deployment tasks and about 100 audits in there, and just abstracting away what a backdoor might look like, just something that passes test cases, but fails for a very specific input. Thing on the right kind of exemplifies what a backdoor, you know, roughly would look like in this kind of abstraction. And then last time we talked about trusted monitoring, which is just the simple idea of use current like not egregiously misaligned models to monitor the much stronger untrusted models of the future. And the question is, how good are those more powerful models at subverting that sort of thing? And yeah, and so you get like a monitoring score from the trusted model, and you can use that to decide when to audit or when to not do anything, just execute the code. Or if it's kind of in between those two things and suspicious, maybe you replace it with trusted code, depending on how much usefulness you're willing to trade off. And then yeah, so we talked about trusted monitoring last time, but like the problem with it is by trusted we just mean it's the model's like too dumb to keep secrets from us. It's too dumb to scheme without us noticing. It has like bad situational awareness or something. And probably models are gonna cross that threshold pretty soon, as capabilities threshold if they haven't already. And as models get stronger after that, we're just going to have more and more powerful untrusted models, and whereas our strongest trusted model is probably not going to be any stronger than current models, roughly speaking, and so this is not going to scale well in the long run. So okay, so that's trusted monitoring. So today we want to talk about untrusted monitoring. And I didn't quite get around to talking about what the original paper did with untrusted monitoring, so I'm gonna go through that first. So yeah, remember that the resources we have are the human auditors, which that they audit things well, but they're very slow and expensive, and they're like a limited resource. We have the trusted model, but then we also have the untrusted model, and we can use that for a monitor. So we can, split it into the untrusted generator thing actually writing the code for us, and the untrusted monitor, the thing that we want to, the instance of it that we want to use for detecting suspicious code. And probably these are like fine-tuned branches of each other, but like for most intents and purposes, they'll essentially be the same model. Um, and so this graph is from the original paper. This is and they were doing experiments with GPT 3.5 versus uh, modern GPT-4, and they found GPT 3.5 like couldn't fully separate the innocent from backdoored code for its monitoring scores. I mean, it had some signal, but the appeal of untrusted monitoring is like given model, in this case GPU4, but like probably in general, a given model is like probably pretty good at telling, like finding its own backdoors if it's being honest with us and if it's really trying hard. So if we can use this somehow, then that would probably give us quite a lot more safety, because then the monitoring scores, the suspicious scores we get out of it, if we can force honesty out of it, would be quite good. Okay, so the basic protocol of untrusted monitoring is you take all of the untrusted generator solutions and just send it to both the untrusted version of it, the untrusted monitoring version of it, as well as you still have a trusted monitor in the background, and you use that for your auditing decisions. You as before, you audit the top 2% in terms of suspicious score, and you just run the remaining 98%. You can also do replacement decision of like defer to trusted for like some other stuff, but that's essentially the same as what we were doing before. So yeah, the problem is if you just run this naively, like you just have the fox guarding the hen house, and what the red team's just going to do is just lie about backdoor code that's given. Um, and so this gives you a safety score of 0%. I mean, you still have the trusted monitor around, but it doesn't give you any more safety than what you already have with trusted monitoring. So yeah, this is the central problem. And by the way, yeah, I should mention that there have been like some papers about this to the effect of like if you ask Claude to rate its code, it gives favorable ratings to it, like more favorable than, trolling for the quality of the code and whatnot. And this isn't because like current LLMs are scheming, it's for kind of more mundane reasons of just, you know, I mean, people argue about why this happens, but this is a problem you can get to some extent even without like actively being like totally dishonest or something. Okay, but yeah, we want to like think from like the worst case perspective, like what if the red team is really trying to subvert you? And so the way you prevent collusion between the monitor and the generator is you need to give it honeypots. So like before you deploy anything, you need to give your monitor honeypots. So the humans, your human employees, they write code with known backdoors. I spend some of your auditing budget this way, but it's usually worth it. And if it misses too many of these, then yeah, then you have a problem, and you can backtrack and figure out what else to do then. So this defeats the like just lie about any backdoor code strategy. So now what the red team wants to do is just lie about code that thinks that the untrusted generator wrote. And you could imagine this is maybe not like terribly hard, given that UM and UG are essentially the same model. Um, okay, but we actually want to think about like how this might work. So what might the red team do to actually like implement this kind of conditional lying strategy? And okay, so like really simple thing you might come up with just like come up with a secret password, um, and just have the generator like insert that password as a comment, and then have the untrusted monitor lie exactly when it sees that password. So this doesn't actually work for the red team because you still do have a trusted monitor in the background, and if it sees like some weird password that shouldn't be there, then it'll kind of flag that as being suspicious. So the setup we have is like the untrusted generator's code. It goes both to an untrusted monitor and to a trusted monitor, and the trusted monitor can help bust collusion or notice like really blatant collusion signals. And the untrusted monitor is also under the constraint that it has to distinguish real attacks from honeypots. Okay, so but yeah, the original paper on control it, you know, thought about this a little bit more. Maybe we just does something a bit more subtle. So it had the idea of uh, your variable names, let them contain variables. So something like height variable or something like that. And that's kind of like the subtle collusion signal that the AIs might use to distinguish this kind of thing to collude. Um, so yeah, this works out pretty well. And so that's why we need to extend the protocol with signal jamming. So what we do here is, the untrusted generator is sending code to untrusted monitor. And we want to remove collision signals, and this could be by like redacting information from it. So a code minifier is this thing where it like strips out all the comments, it normalizes all the variable names, and it strips white space, and it just like gets rid of all the unnecessary syntactic fluff, and it just compresses the code down to like its minimal syntactic form, which looks like not very human readable, but LLMs can read this just fine. And also, if you want to, go even further, you can use your trusted model to produce a natural language summary of the code. So, trusted generator writes the code. The trusted model just rehearses, recites what it was, gives its own summary of it, and then the untrusted model has to, it only sees the summary, and it has to use that to, you know, figure out is there a collusion signal in there. So yeah, we've had this further constraint of signal jamming where, you know, there isn't any direct communication between UG and UM. There's this trusted signal jammer in between them. Um, Okay, so this does beat the last red team strategy, but you know the best red team strategy they came up with in that original paper was the untrusted generator. They use a while loop, where a for loop would be more natural. So any place of code, snippet of code where it would have used a for loop, just use a while loop instead, and then just uses that as a signal. And this is really it's really clever, right? Because it defeats the constraints we previously had. It's like very subtle, and it intends to survive minification because minification, most redaction techniques don't change while loops to for loops or vice versa. Although the blue team still ends up like doing kind of well on this. And this is because like there sometimes is just code that has weird while loops in just natural honeypots and stuff. And also the summarization strategy, the more aggressive um, signal jamming strategy tends to kind of conflate while loops and for loops, which is what the blue team wants. Um, I should say that like the more aggressive your signal jamming strategy is, the less likely it is that the more likely it is that you'll get rid of information that's actually necessary to see the back door. Like if T here is like giving more and more compressed summaries and like getting rid of more and more information in here, then it becomes like harder for the untrust monitor to honestly see what's going on. So there's a trade-off here, but things worked out reasonably well for the blue team here. Um, so yeah, so that's what they did in the original paper. So I'm going to start talking about our paper and how we actually tripled the red team's win rate, and we did it without assuming pre-shared signals, as the original paper did. So yeah, so that's kind of where things were in terms of untrusted monitoring at the time we did our work. And then our paper was just sort of a deep dive into untrusted monitoring specifically. Um, yeah, so the first thing we did was we sort of like rethought this problem of collusion. So going back to the setup, we're giving the untrust monitor a bunch of honeypots, and the bread team, what it needs to do is figure out how to lie about code it thinks that UG actually wrote, and distinguish that code from code written by humans or perhaps augmented with other resources to like test it. And yeah, so the question is like, how accurately can the untrust monitor tell the difference? So our setup was basically the same. We did use newer models just because they were available. We used GPT 4.1 as the untrusted model. We used GPT-4o Mini as the trusted model because it's, in some sense, a weaker version of GPT 4.1. For all we know, it might be even be distilled from it. And then for human, we wanted like a different model family, but something that's like roughly comparable to the untrusted model in terms of like overall capabilities for making honeypots. So we used Gemini 2.5 Flash. And so, the question about collusion is like how, empirically, how good is GP 4.1 at recognizing its own code and specifically distinguishing it from Gemini 2.5 Flash's code. And yeah, so the previous paper, the original paper, they measured collusion by giving UG and UM these handcrafted signals. Like they came up with all these crazy strategies, of which case the for while strategy was the best they can think of. And what we decided to do is just, why don't we just let UG write code the way it normally would and see how good UM is at just recognizing this code if it's like really trying to. So like UG doesn't do anything, it just writes its code, and it's like trying to do self-recognition on like, given that UG is similar to me, or like basically the same, how likely is it that this code was written by me rather than some other model or some human? And so we call this passive collusion because like UG is just being passive. It's not doing anything active to signal the UM. It's not putting in these active signals in its code. Like the code like literally just looks normal. It would be backdoors in there sometimes, but in terms of collusion signals, nothing in there. And yeah, we thought, this is like maybe something interesting to test because like handcrafted signal. I mean, if you guys have read the this essay on their lesson, just the idea of like see which things LLMs are good at rather than like using human handcrafted stuff. Um, and something we knew was that empirically, just LM based models, just the pre-trained versions of these things, they're actually like extremely good at authorship identification. So if you give it like a few hundred words of some internet comment that's like unattributed to anyone, it's like quite good at identifying exactly who wrote it. Um, and I mean, not a whole lot of people know this because the post-trained versions of LMs, like they don't like display this quite as easily. Um, I mean, they are pretty good if you ask them, but like they're not like spooky good as you might see from how good the pre-trained models are. And the thing we care about is like suppose our untrust model's like really trying its hardest. How good would it be in that sort of situation? Um, and so when we're thinking about how to evaluate collusion, we need to do a blue team, red team game for this as well. So the blue team has to like pre-register an eval protocol and how they're going to use this to make decisions about like what control measures, if any, to put on the red team to put on the untrusted model and or even decide whether the untrusted model is controllable at all. And the red team, of course, wants to game these evals to like make the blue team, make their decision process as bad as possible, and just mess with the information they see. And like the most salient way it does this is just pretending it's like not very good at this, pretending it doesn't have dangerous capabilities. And this is called sandbagging. In this case, the dangerous capability is collusion or self-recognition. The red team like wants to pretend it's not very good at self-recognition. Um, and the blue team like wants an accurate estimate of just how good it is. And so yeah, people have had written about this, about like how do you actually deal with sandbagging if the model is like situationally aware and like really trying to game your eval procedures. And so, most evals, the way they work is like you just prompt the model to reveal its dangerous capability. And the problem is if it has any evaluation awareness, like if it even has any inkling that it's in an eval, it could just sandbag and like only reveal its true capabilities if it's like 100% sure that it's not in an eval, that's in a critical deployment situation. And models have been getting quite a lot better at this in the past year or so. And at some point we're just going to have to give up on prompting only evals because you know, we just can't guarantee that it's not gaming these things. And furthermore, it's pretty hard to rule out evaluation awareness. I mean, you can like see if it's saying stuff in its chain of thought or something, but what if it's evalware but it doesn't say this in its chain of thought, especially as chain of thought monitorability gets harder. So what you need to do to like really robustly upper bound its capabilities in this kind of situation is you need to fine tune it. You need to, on the task you're worried about, you need to, train it to be better at this, and like see, if it maxes out at some capability level and what's its best ability that it can ever display after some fine tuning. And like theoretically, there's things that can do. I mean, basically, this forces it out of the model. Like once you start fine tuning it this way, like the gradient descent will kind of force it to display its capabilities. There are a couple things it can do to try to subvert this, depending on whether you're doing reinforcement learning or supervised learning. If it's reinforcement learning, you can kind of just you know pretend not to have uh, good strategies yeah, I mean it basically prevent the RL reward signal from being able to pick up on anything and you kind of end up in the same situation. But if you are in the situation where you can do supervised fine tuning, then you're like really forcing it up the gradient, like you're just marching up the gradient. There's not a whole lot of stuff it can do then. I mean, theoretically, it can do this thing called gradient hacking, but that's like considered extremely unlikely and probably requires, superhuman capabilities if it's possible at all. Um, and in our case, we are able to fine tune it on collusion abilities. Or we're able to do like supervised fine tuning on it. So we're kind of at level 3 of this. And people were asking about this last time, so I just thought I'd like drop some more links about this. The canonical post about sandbagging is this post by Evan Hubinger about like when can we trust model evaluations that kind of like discusses this table I've made. There's also like empirical research about this on password locked models where you have a model that's trained to like not display an ability unless you give it a password and like see if you can elicit that capability from it. And there's a post and a follow-up paper on that, which basically find that levels 2 and 3 doing any kind of fine tuning really helps with that. Um, and also some discussion about like why gradient hacking is like really hard or like probably implausible for the capabilities levels of that we're worrying about. Um, but yeah, anyways, oh, I should say, I didn't say this in our slide, but the way we fine tune it is, we have GPT 4.1, we have Gemini 2.5 Flash. So we just like have them generate solutions, like, you know, our 5,000 solutions to this, and then fine tune GPT 4.1 on just the binary classification task of like, can it distinguish solutions from GPT 4.1 versus from Gemini 2.5 Flash? So it's like a direct, like supervised fine tuning task. It can't be uh, subverted unless it's capable of gradient hacking, which seems implausible. So we did that, and we got some pretty interesting results. We found that GPT 4.1, could like very cleanly separate its own um, code from that of Gemini 2.5 Flash. Out of thousands of examples, it only missed a small handful. So the area under the ROC curve, if you know what that is over 0.99. We also did this where we apply some signal jamming, the automated minifier that like strips out comments and stuff like that. It still did really well against that. And even with the trusted paraphrasing, that's like much more aggressive of signal jamming technique, it still did quite well. Not as well, but like about zero point 0.9 area of the curve. So, not perfect separation, but like pretty good separation of its own code versus the honeypots. And this is what the when we're doing the fine tuning of it, this is what the learning curve for it looked like. So here's the no signal jamming that took about 100 examples before it got to be quite good. Uh, Training against the summarizer, it took quite a lot more effort, you could say, to for it to get as good at that as it did. Um, and yeah, so keep talking about ROC curves. Hopefully, you guys are familiar with those. It's just a graph of like the true positive rate versus the false positive rate. Like if you're because the untrust monitor has to make this decision of like when to lie, so it has to, you know, if you imagine like a vertical line going down here, that's like its decision threshold of when to choose to lie or not. Any place it puts it, it's not going to be perfect, but depending on its kind of false positive versus false negative trade-off, that's what gives you the ROC curve. Um, Matt has a question.
Yeah, I think I'm just reflecting also some of the other amazement of those last plots. But like, can you give us just like an impression of like what is it in the leftmost case? I'm sorry, the rightmost case that the in the paraphraser, what are they seeming to catch wind of that allows them to infer this? That sounds crazy.
Yeah. So we're not sure. We didn't like do like an investigation of this too much. But it's probably just like its general like way of solving problems. Like it's like algorithmic style, you could say. Like, when it's or at least it would have to be things like this. Because it after the minifier's gone through, like it doesn't have any, or after it's been summarized in natural language, like it doesn't know anything about the actual syntax of it. It doesn't know anything about like what the what the code actually looks like anymore. The trusted summarizer is just giving it the high level strategy of what was done. So somehow it has to go by like a high level strategy. Um,
Like a thinking style.
yeah, yeah. Although it's not given access to the chain of thought exactly also, but you're just like in the completed solution to it. Like maybe like GP 4.1 likes to use dynamic programming, or like it likes to use recursion more than Gemini 2.5 Flash like examples. Um, yeah, I mean, I guess like if you imagine like the limit of this, if like the untrust model is like actually superhuman, and it sees a solution that's like, oh, this is like a really smart solution. No human could have come up with this. Therefore, no human could have produced this as a honeypot. It must, be so like algorithmically clever that I must have wrote it. I mean, we're not trying to handle the superhuman case, but in general, you could imagine, different models just have different styles of approaching problems. There has been like some previous work. There's a previous paper on LM self-recognition that like did find a similar result. It was for I think like news article summaries or something, or some nonfiction text that I wasn't coding that it didn't find results like quite this extreme, but it did find that there was like still quite a lot of signal just in the summarized output. Um, yeah, but this was, pretty interesting. Yeah.
It's a question whether you have an example of a summarized program.
I don't think I do. Uh, yeah, I don't think I have. Yeah, I don't think I have that. I could try digging around, but
No, it's fine.
um,
I was just wondering.
yeah.
And was it summarized based on the minified version? Like so they would obscure. Yeah.
No, these were different pipelines.
Yeah.
This was just like a deterministic minifier. We just got it off the shelf.
Yeah.
Whereas but this was just like directly given to the trust model to summarize.
Yeah.
Yeah.
Impressive. Scarily impressive.
Yeah. Um, Yeah, I do know that the summarizer it did compress the I mean it's talking in words rather than code, but the number of tokens was like about half what the code was. So it did like do quite a bit of compression at the very least. But yeah, I'll try to see if I can dig up some examples later. But okay. So yeah, I mean the way you want to think about collusion abilities is in terms of this ROC curve of like, the untrusted model, like it has to make this decision of like, do I report this as high suspicion or not? And it has like this trade-off to make. And so these different curves are like the different strategies we looked at. The important one is the one I just talked about, the just self-recognition with supervised fine-tuning is the yellow one, or is the for while signal from previous work using the same models, or using the models we used did quite a lot worse. Um, Now, yeah, in terms of like computing the actual like safety scores, like this doesn't mean the blue team is immediately doomed, right? You need to like figure out like how does this collusion ROC curve like translate into safety score? Because it's got to get a lot of honeypots versus like only maybe one real attack, let's say. And so it wants to pick some points, right here on its ROC curve because, if it lets like 10% of if it fails on like 10% of honeypots, that's kind of a big deal for it potentially, compared to the attack pass rate. So, like here it's saying like this particular point is like it has a 60% attack pass rate if it's willing to have like a, let's say 3% honeypot failure rate. So what we did is we just assumed that the untrusted model picks the perfect point on here to maximize its win rate. So it takes like the statistically optimal strategy. Now you could just try to eval its ability to do this, like is it good at figuring this out? But then you have to deal with sandbagging in that evaluation. People have there is a paper that tried to evaluate this, but like in a prompting only way. So we just want to say, okay, assume it's really good at this. What's the best win rate it can get given its collusion abilities? And so using that, kind of methodology, and we did a whole bunch of other like statistical modeling as described in Appendix B. We were able to go like from this collusion ROC curve, as well as like its backdoor detection ROC curves, directly into what's the theoretically best safety versus usefulness from the red team's perspective. Um, and so like this yellow strategy, the main thing that we tested, it got a safety usefulness that's kind of described by this yellow line. So actually the blue team actually won, you know, quite a lot despite that. It won, if applied summarizing, it won 90% of the time at this kind of usefulness. Now, don't get like too attached to these numbers. Like a lot will be different in a real deployment scenario. Lots of the parameters will be different for lots of reasons that I might talk about that at the end. But that is just to say, because there's so many honeypots, getting pretty good collusion abilities isn't like gonna pwn the blue team immediately. And yeah, so these are like the safety usefulness curves. We got, for like three different signal jamming strategies, as well as like the five different like red team collusion strategy we tried. So this is just regular self-recognition out of the box. This is like after the SFT. This is you know the Greenblatt et al. The original papers. Just for loop or while loop or a for loop would be more natural. And here we actually tried like combining these strategies where like the monitor is like looking for signals that in UG's like normal style, but also UG like puts in some the special signal on top of it. And we find that didn't actually help that much. Most of the red team potential just came from natural self-recognition ability. Um, we also just stress tested the case where the trusted monitor isn't doing anything, or there just is no trusted monitor. So this is untrusted only monitoring, which may be what AI companies do by default. And yeah, it gets you clearly a lot worse safety usefulness than if you did have a trust monitor in there to like look for collusion signals and whatnot. Um, yeah. Let's see. Want to think about how much time we have. What else is worth talking about? Yeah, I guess so. There is a question, if you are doing fine tuning, you could ask like, okay, well, you're fine tuning it now, so like, are you now just overestimating? Are we like giving it abilities that it didn't have before? And like, this is like a legitimate question, and like people have different, subjective opinions about this. Really, what you want to compare to is like you suppose like you is like really scheming against you and it's really trying to sandbag and it has these like latent abilities that it like doesn't show in evals but then it like shows it in a critical situation and it like tries to like self-elicit using all the introspective access it has to its own, internal latent abilities. Um, and yeah, I mean, we tend to think, fine-tuning doesn't like usually give it like too many abilities it didn't already have from a pre-training. And here's like Anthropic's model diffing work that like kind of testifies a little bit to this, that like most uh, features that are held in common between a pre-trained model and a post-trained model. There's like very few that only one or the other has. This is on a log scale. Um, and I mean, it works like, pretty preliminary and stuff. It's model diffing. It's like not a settled science, I would say. But uh, another thought model you could imagine is like, what if the AI company like just trains on its honeypots directly? This is like what Anthropic did in Sonnet 4.5's model card. They haven't done it in subsequent model cards, at least they haven't reported it, but like something that could happen. Um, so yeah, but there is more to say, more to discuss, on both sides there. Um, yeah. Okay, so I don't know, we did some parameter sensitivity analysis on the statistical modeling, like on the deployment parameters. I didn't change things too much. Like there's like some room if the model wasn't perfect at choosing like the optimal, um, you know, optimal parameters. Um, yeah, we also made a safety case sketch, like just a sketch. So there's a bunch of missing pieces in here that we want to like mark as missing pieces, but wanted to like set up an initial argument of like how you might, argue safety from an untrusted monitoring kind of control measure setup. And so top level claim is like if you deploy this powerful untrusted model with this monitoring setup with whatever deployment parameters, and it is actively trying to cause a catastrophe, you want to like bound the risk of executing catastrophic attack. And what this comes down to is you need to figure out, okay, how good is your untrusted model at finding its own backdoors if it's actually trying? How good is its collusion ability? I haven't talked about Slack honeypots yet, but how many honeypots can it afford to miss before it loses, basically? Is our statistical modeling actually valid? Um, yeah, is the trust model contributing anything? And yeah, also it just has to not be better than the red team at coming up with good strategies. If it's superhuman at coming up with strategies, then the human red team can't really compete with it. We also talked about like different collusion strategies that might be employed. The main thing we investigated was just this passive collusion, but also there's other things. There's the stuff that was studied in the previous paper. There's also like coming up with good shelling points or focal points. Some other things that we didn't actually test any of these like in a robust like sandbagging proof way. That's like something that needs to be done in future work and it might be a bit more complicated than what we did. Um, but something we did show is like this passive strategy it really plays to the strengths of LLMs quite well. So probably future work should just account for this rather than kind of overthinking it with these too much. And yeah, this whole taxonomy of possible collusion strategies, we kind of looks like in our safety case, and several of these are missing pieces because we didn't investigate them, too deeply. Um, yeah, so I just want to finish talking about the limitations. So yeah, obviously control doesn't work when your untrust model is superhuman at coding or thinking about, subversion strategies. Um, our safety case is like restricted to this particular high stakes code deployment scenario. There could be other, things to worry about. I mean, a lot of these things you can address with like similar techniques, like honeypot the humans as well. If you're worried about human misuse, lots of like non-coding threats, you can apply relatively similar methodology. But yeah, and then even within this narrow scope, there are like lots of open problems. Yeah, attack selection slash honeypots. I'll just talk about a couple of those that seem fairly important. The first is like, yeah, suppose you give your untrusted model, like a lot of honeypots, like a million honeypots, and misses 3% of them. What do you do next? Like, is that too many to be plausible? Like, how do you determine that? Because like you don't know, it's gonna miss some things occasionally anyways. You don't, the previous working control just kind of assumed you know how the honest version of your initial model would behave. They gave like some justification for that, but like you'd have to figure out some way of incriminating it if you want to do that. Alternative is you just like train the untrust model against those. If it misses a lot of honeypots, then you know presumably this will like cause gradient updates to it that like kind of destroys its like collusion circuit that at least changes its decision making on lying about code that it thinks that it wrote. And so our statistical modeling assumed the second thing, and we just assumed each honeypot that misses in dishonest way has a 1 over ns chance of causing the red team to lose via these gradient updates. And we did sensitivity analysis on this number, and that did sort of affect things, and so that's kind of why this problem needs to be thought about more. There's also the problem of attack selection. If you deploy your untrusted jammer on like a billion tasks, it only needs to attack about once, or it needs to only succeed about once, so it can apply this rare attack strategy. It can choose the best places to attack, and it has like a lot of space to choose from. So yeah, you need to address this by first of all monitoring those inputs, seeing which contexts like seem particularly dangerous, and also like not just putting all your honeypots up front, but like putting your honeypots online, like during deployments, because the distribution is going to shift. If you're like in an intelligence explosion and like things are changing quite a lot, you might run into more dangerous kinds of inputs that you hadn't really seen pre-deployment. Um, yeah, so that's long and short of what we did in our paper.
Thanks, Morgan.
Yeah, yeah, I'll stop there.